We are in chapter 3 where we are discussing torsion. This is the 15th session overall and the third session involving torsion. Here we'll first look at some examples involving angle of twist. Then we'll discuss transmission shafts, statically indeterminate cases, and stress concentration factors. Finally, we'll look at some examples involving these three issues. This map using block diagrams give us an idea of where we are. In the first two chapters, we discussed basic concepts and axial loads. We are in the third chapter involving torsion, and as we can see, we are midway. This problem is similar to the previous problem. We have two bars, AB and CD. There's a gear at B and the gear at C. The diameter of the gears are given and the diameters of AB and CD are also given. The length of AB and CD are given as well as the torque and the G of the material. From the diameter of gear at B and C, we can find out the ratio of the torques in B and C. So the torque in C is 1.33 times the torque in B. Also from the diameters we can find out the ratio of the rotation in B and C. So the gear in B will rotate 1.33 times more than the gear in C. So here the ratio of the torque is given and we know the torque in AB, so we can find out the torque in CD. And here the ratio of the angle of twist is given. So to find out torque, we have started from this end and we have found out the torque in CD. To find out phi, we start from this end. Phi at D is 0. So we find phi in CD and as such phi in C. So phi CD is found here. Torque in CD we have found earlier and we know L, G and J. So this is the value. This is the value of the rotation of C. Now the rotation of B would be 1.33 times the rotation of C. So we find the rotation at B. Now we know the rotation at B. We'll find the rotation in BA to find finally the rotation at A. So here we have found out the rotation phi PA. So this is the torque and we know L, G and J. So this is the value. Phi A is given by adding phi B and this value which we get in radians, which we turn into degrees. Here we have a problem that is similar to the last two problems. A torque is applied here and we are given the radius of the gear P and gear C. We are not given the radius of AP and CD, which are equal. We are given the maximum shear stress and the maximum rotation. So there are two limitations. One is the rotation and one is the shear stress. we are required to find the diameter of AB and CD. So we'll find the diameter of these two bars using the two limitations one by one. First, we'll find the diameter using rotation, and then diameter using the maximum shear stress. Whichever diameter is larger will govern. The ratio of the radius of the gears is 2.353, so the torque in gear B is 2.353, the torque in gear C. And the angle of rotation of gear C is 2.353 times the rotation of gear B. Or in reverse, we can say that the rotation of gear B is equal to 0.425 the rotation of gear C. To determine torque, we start with this end. So the torque in CD is this value, and the torque in AP is this value multiplied by 2.353. To determine rotation, we start point A where the rotation is 0. We do not know the J of AP, so we find the rotation in terms of J. So here 5BA is given as the torque in AB multiplied by the length divided by G into J. Since the rotation at A is 0, this is the phi at B. The phi at C would be 2.353 times the phi at B. So multiplying, we get phi C in terms of J. We now know the phi of C, so we'll find out the phi of CD to get the phi at D. So here phi CD, the torque is this torque, and the length is given, and G is known. So we find phi CD. Phi D is the summation of phi C plus phi CD, which we find in terms of A. We are given the maximum rotation, which we turn into radians, and from there we find J and the radius and diameter. Next, we find the diameter using the maximum shear stress criteria. The torque in AP is higher, so we use this torque to find out the required diameter. So in this equation, we know mass, we know E, so we can find out J divided by C, from which we can find out the radius and the diameter. We see that the diameter related to the rotation criteria is higher, and as such will govern. Here we discuss transmission shafts. Force multiplied by distance give energy. Energy transmitted per second is power. In case of a body subjected to a torque, torque multiplied by rotation gives the energy. Energy transmitted per second gives power. Thus, power can be given as torque multiplied by angular velocity. If the frequency of rotation of a body is given as f, then the total angle covered is 2 pi f per second. So the angular velocity is given as 2 pi f. So power is equal to torque into omega, where omega is given as 2 pi f. So power is given as 2 pi f p. Now consider this example. The frequency is given, the material properties is given, and the maximum allowable stress is given, along with the geometry. We are required to find the power transmitted and the angle of twist. So first of all, this is a hollow section, and we can find J of this hollow circular tube. So we have found out J. Now we are given the maximum shear stress. Using the maximum shear stress, and since we have the geometric parameters, we can find the torque or the maximum torque that can be applied. The frequency is given in RPM or revolutions per minute. Dividing that by 60, we get the revolutions per second. And P is given as 2 pi ft. So we have just found out P. So we can find the power. The angle of rotation of a shaft of constant cross-section is given as earlier by TL divided by GJ. So we know T, we know L, and also GJ. So we can find out the angle of rotation list. In this problem, we are given the power that is transmitted and the frequency of rotation. We are asked to find out the maximum stress in bar AB and CD, which are of the same diameter. We are given the diameters of B and C. So that means we can find out the relation of torque between B and C. Now, given that we have the power and the frequency, we can find out the torque in AB. So torque in AB is power by 2 pi F. So we know the torque in AB. And since we know the diameter, we can find out the maximum stress in AB. Now we expect the torque in CD to be higher, so we multiply the torque in AB by the ratio of the diameters of C and B, and we get a different torque for CD. Now again, since we have the torque in CD and we have the geometry, we can find out the maximum stress that is acting in CD. We are given this arrangement where we have a disk at B and a disk at C, and they are connected by a strap, and we are given the geometry, that is the radius of AB and CD and the radius of the disks. We are also given the maximum shearing stress that is allowed. and the power. So we need to find out the torque, the maximum torque that can be applied, and the frequency of rotation corresponding to it. This arrangement has similarity with the case of two gears adjacent to each other. In the case of gears, the fact that the magnitude of the force exchanged between the gears are the same give us a relationship between the torque in the gears and their radii. Here we see that the same strap goes around the disc B and C. So the tension in the strap will be constant, which means that the force applied in B and the force applied in C will be the same. Thus, the ratio of torque in B and C would be equal to the ratio of their diameters, as in the case of two gears adjacent to each other. We also see that as these two disks rotate, the distance of contact of disk B and disk C will be the same. This means the angle of rotation, the ratio of the angle of rotation of disk B to disk C will be the inverse of the radii or the ratio of the radii. Hence, both relationship of torque and angle of twist is same as that of two adjacent gears in this case. We now find the maximum torque that can be applied. So either the bar AB will fail first or the bar CD will fail first. Let us start by considering failure of the bar AB. So here we have taken the maximum shearing stress and we know the geometry and we have found out the maximum torque that can be applied in AB. Now the ratio of diameters of the disk at B and C is 4:1. So the torque in C will be 1/4 of this torque in AB. So using that torque, we can find out the stress in CD. That stress comes out to be quite low compared to the maximum allowable shear stress. Hence, if this torque is used in AB, both AB and CD will not fail. Let us now consider the maximum shear stress allowed in CD. Then if the maximum shear stress is used, we know the geometry of CD, then we can find out the torque that can be applied in CD. Now if this torque is applied in CD, then the torque in AB would be 4 times this value, which is much greater than the maximum torque that can be applied in AB. So if this stress, the allowable maximum shear stress is considered in CD, then AB will fail, which means the maximum torque that can be applied is this value. Now that we have found the maximum torque that can be applied, we can find out the the rotation of AB and CD. We first find out the rotation of AB. We are given the power and we have found out the torque, so we can find out the frequency. Now, the disk at C will rotate 4 times faster. So, whatever we have found, we multiply that by 4 to get the frequency of rotation of CD. Here we discuss statically indeterminate cases in torsion. We have earlier discussed statically determinate and statically indeterminate cases in bars subjected to axial loads. In statically determinate cases, the external reactions could be found out using the equation of statics. From the external reactions, we could get forces acting in internal sections. We could then determine the stresses acting on these internal sections along with strains and deformation. The strains were found from the stresses using Hooke's law. In statically indeterminate cases, the equation of statics were not enough to find out all the external reactions. We used equations involving conformity of deformations. Substituting displacement force relationships into displacement relations, we could turn them into force relations. These extra force relations, along with the equation of statics, were enough to determine the external forces. Once the external forces has been determined, we could carry out the analysis similar to statically determinate structures. Thus, we could find out the internal forces, then the stresses, strains, and deformations. When it comes to torsion, we have dealt with statically determinate cases till now. However, statically indeterminate cases in torsion can be dealt with similar to the cases of axial bars or bars subjected to axial loads. The equations of statics are not enough to solve statically indeterminate cases in torsion. We use relations of angle of twist to find extra equations. We earlier determined a relation of angle of twist involving the torque applied. We can substitute these equations in equations of angle of twist to find relations between torques. These extra relations added to the equation of statics are enough to find out the external torques applied. With the external torques known, we can find out the torques in internal sections, the shear stresses, the strains, and the angle of twists of members. Now consider an example. Here we have a bar that is fixed at A and B. A torque is applied at C. So there will be a torque at A and a torque at B, resisting this applied torque. So from statics we get TA plus TB is equal to torque applied at C or P. Here we have two unknowns, so we can't find the external reactions TA and TP directly. Now consider a section taken between A and C. Then considering from the left-hand portion, the torque acting will be PA. And consider another section taken between B and C. Now considering from the right-hand portion, right-hand side, the torque acting on the section will be TB. Here A and B are fixed, so the rotation at A and B is 0. If we move from A to C, then the bar is twisting and we can get phi AC. If we move from B, again the bar would be twisting and we can get phi BC. Now the twist at C is the same, so that would mean phi CA is equal to phi CB. So this is the extra equation of deformation we were looking for. Now phi CA can be given with this equation. The torque here, as we earlier discussed, is TA. Phi CB is given by this equation. The torque, as we earlier discussed in CB, would be EB. So we can substitute these two relationships in this equation and we get this expression. Where knowing LAC and LBC, we have a second relationship between TA and TB after this relationship. Hence, we can find TA and TB. After we have found TA and TB, we can use these two relationships to find the angle of twist. Here we have a composite structure of steel and aluminum to which a torque is applied. The core of this circular bar is made up of steel and the outer sleeve is made up of aluminum. We are required to find out the maximum torque that can be applied along with the angle of twist. The modulus of rigidity of aluminum and steel are given, and the allowable stress in aluminum and steel are also given. We see that if we apply a torque E here, then the torque will be taken up by the steel core and the aluminum sleeve. So we have two unknowns, and this is a statically indeterminate problem. From deformation, however, we can obtain a relationship between the steel core and the aluminum sleeve. They will twist by the same amount. So we can find the torque in the aluminum sleeve and in the steel core if we knew the amount of torque applied. This is the deformation equation, and we first find out the J in steel and the J in aluminum and put those in the equation for phi, L in this case is the same for both, and we find out a relationship between the torque in aluminum and the torque in steel. We next find out the maximum external torque that can be applied. To find out the maximum external torque, we first take the steel inner core. So we have the allowable stress in steel and we have the geometry. We can find the torque that can be applied to the inner core. That is the maximum torque. Next, we take the aluminum sleeve. We have the allowable stress and we have the geometry, and we find the maximum torque that can be applied to the aluminum sleeve. Now from this equation we see that the torque in aluminum would be 1.37 times the torque in steel. So if we consider this torque, which is the torque in steel, and we multiply it by 1.37, then we get a value which is quite higher than this value. So the component will fail. On the other hand, if we take this torque, the maximum torque in the aluminum sleeve, and divide it by 1.37, then we'll get a value quite less than this value, which is the maximum torque that can be applied in steel. Hence the component then would be safe. So the torque given by considering failure in aluminum is the maximum torque that can be applied. Dividing this torque by 1.37, we can find the torque that will be applied to the steel core. Adding these two up, we get the maximum torque that can be applied overall. Angle of twist can be found out using either aluminum or steel. Here we have used the aluminum case. So we have taken the torque in aluminum and we know length G and J, and we find out the degree first in the angle of twist first in radians and then in degrees. While dealing with statically indeterminate cases of bars subjected to axial loads, we dealt with cases where the deflections were equal and the deflections were summed up to zero, among other cases. We also dealt with misfit cases where the difference of deflections was a finite value. With statically indeterminate cases in torsion, we have already dealt with case where the angle of twist was equal. Here we deal with the misfit case where the difference of angle of twist is a constant value. Here we have two bars AB and CD, and the discs at B and C are attached by bolts. Now, the disc at B has to rotate by a given angle till both the discs B and C start rotating together. So this is a misfit problem involving angle of twist. Now torque is applied to the disc at B, and there will be reaction torques at A and D. So from statics we get TA plus TD is equal to P, which is the torque applied at B. As earlier discussed, the bar AB has to rotate by a small angle before AB and CD start rotating together. So phi BA is equal to phi CD plus that small angle. So here we have two unknowns and we have one equation here from statics and another equation from compatibility. We now find phi BA in terms of TA and G and phi CD in terms of TD and G, though we are given G. We substitute the phi BA and phi TA in this equation, and we also substitute the value of G. We get an equation as shown here. So we have already got this equation. Putting the value of T, we have these two equations. From these two equations, we find out the value of TD and then the value of A. We're asked to find out the stresses in the two bars, AB and CD. And since we now know the torques and we know the geometry which is given, we can find out the stresses in the bars. Here we discuss stress concentration factors of components under torsion. We have earlier discussed stress concentration factor of components subjected to axial loading. If a component has a discontinuity, then the stresses around the discontinuity are generally higher, and stress concentration factors are used to give these higher stresses. We earlier considered a flat plate with a hole subjected to axial loading. The stresses around the hole is higher than the stresses in the rest of the plate. In components with discontinuities, we need to know the higher stresses since for design and analysis purposes, we use the higher stresses. The definition of stress concentration factor of components subjected to axial loading or torsion are the same. The stress concentration factor is given as the maximum stress divided by the average stress acting on a component. Thus, we find the average stress and then multiply it by the stress concentration factor to get the maximum stress. Stress concentration factors are obtained using the mathematical theory of elasticity or experimental methods such as the photoelastic method. They are given in tables or graphs as the one shown here. Stress concentration factors are found to be dependent on ratios of geometric parameters and not on dimensions or the material of a component. Here we have a bar that certainly changes the diameter and it is subjected to a torque. This diagram shows a vertical section. D is the diameter of the larger portion or the portion with the larger radius. Small d is the diameter of the portion, the smaller radius. There's a fillet in between the two parts of the bar. The stress concentration depends on two geometric ratios. The first one is big D divided by small d, that is the ratio of the diameters. And the second one is the radius of the fillet divided by small d, the diameter of the portion with the smaller radius. So let R by d be 0.2 for a given specimen, and let big B by small d be 1.25. Then, as we can see, the stress concentration is slightly higher than 1.2. To find the maximum shearing stress, we first use the formula dr divided by j on the portion with the smaller diameter. We then multiply the stress obtained by P. This gives us the maximum stress. And this is a stress concentration problem. We have a stepped shaft and we're asked to find out the power that can be transmitted. We are given the dimensions and the maximum shear stress. We need to find out the torque or the maximum torque so we can find out the maximum power that can be transmitted. So first we find out the stress concentration factor for this stepped shaft. Here we have R by D as 0.2 and large D divided by small d as 1.25. So this is the curve for large d by small d of 1.25 and R by d is 0.2. So as we can see, the stress concentration factor is slightly more than 1.2. So here we have taken the stress concentration factor as 1.22. Now max is equal to K into the normal stress, but the normal stress is given as Tr by J. So putting in the values, we can find out the torque that can be applied without failure. We are given the frequency, so power is equal to 2 pi ft, and we find out the maximum power that can be transmitted.